Welcome to the genesis of the modern world. This slide introduces Claude Shannon, the playful architect who fundamentally redefined our understanding of communication. The visual narrative captures a pivotal transition, a smooth, continuous analog wave evolving into the precise binary pulse of the digital age. Shannon's own features are etched in the ones and zeros that he championed, superimposed over technical blueprints that symbolize his invention of information. Known for blending high-level mathematics with a legendary spirit of whimsy, Shannon didn't just study data, he gave us the mathematical language to measure it. This synopsis explores how his unique brand of curious genius laid the groundwork for every bit and byte that defines our lives today. Meet the man who balanced the complexities of the universe while riding a unicycle, Claude Shannon, arguably the most influential unknown of the 20th century, was a solitary Bell Labs mathematician who turned the vague concept of communication into a measurable physical reality, the bit. This slide illustrates how Shannon's revolutionary insight serves as the essential bedrock of our modern world. From the core of his genius, we see the branches of his legacy, the global reach of the internet, the logic of AI, the security of cryptography, and even the decoding of DNA. Whether compressing data or sending signals across deep space, Shannon's playful tinkering provided the mathematical architecture for the entire digital revolution. In 1937, a 21-year-old Shannon achieved what many consider the most significant master's thesis in history. This slide depicts the profound bridge he built between three worlds, the physical, the logical, and the digital. Shannon realized that the complex ad hoc wiring of telephone relays could be perfectly mapped to the 19th century symbolic logic of George Boole. By proving that a closed circuit represents true ones and an open circuit represents false zeros, he demonstrated that simple electrical switches could execute complex algebraic equations. This epiphany transformed hardware design from a trial-and-error guessing game into a rigorous mathematical science, providing the fundamental blueprint for every digital computer in existence today. Before 1937, electronic engineering was often more gut feeling than rigorous science. This slide charts the evolution from the ad hoc designs of the past to the mathematical precision of Shannon's switching theory. In the pre-Shannon era, circuit assembly was a trial-and-error art form, producing fragile systems that required constant manual recalibration. Shannon revolutionized this by treating hardware as logic. By mapping Boolean algebra to binary switches, where series and parallel connections represent specific mathematical operations, he turned guesswork into mathematical optimization. This breakthrough replaced mechanical intuition with the foundational architecture of logic gates, marking the exact moment computing moved from the physical clinking of gears to the silent, elegant logic of the digital age. In 1948, Shannon unveiled his magnum opus, a mathematical theory of communication, the Magna Carta of our digital world. This slide maps the journey of a signal from the information source through the transmitter and across a channel plagued by noise to its final destination. Shannon's breakthrough was the noisy channel theorem, the proof that data could be transmitted with near-perfect accuracy despite interference. By treating information as a measurable reduction of uncertainty rather than a matter of meaning, Shannon paved the way for error-correcting codes. The visual contrast between the erratic analog wave and the clean digital pulses highlights the moment humanity learned to master the medium, ensuring every bit arrives exactly as intended. In 1948, Claude Shannon performed a radical surgery on human communication. This slide captures his most counterintuitive leap, the divorce of information from meaning. Using the metaphorical scissors of mathematical logic, Shannon separated the semantic soul of a message, be it a Shakespearean sonnet or a grocery list, from its measurable quantity. Shannon realized that for a machine, the meaning is irrelevant. Only the resolution of uncertainty matters. This birthed the bit, the universal currency of the digital age. As the visual depicts, by stripping away the weight of semantics, Shannon allowed information to flow as a precise binary pulse. It was the moment communication stopped being about how we feel and started being about what we can count. In 1948, Shannon unveiled the Magna Carta of the digital age, the universal model of communication. This slide maps the journey of a signal from source to destination, identifying the essential roles of the transmitter as an encoder and the receiver as a decoder. At its heart lies the channel, where the signal must survive the noise source, represented by that chaotic lightning bolt of interference. Shannon's genius was proving that we can overcome this static through mathematical error correction. The visual transition from a messy analog wave to a precise digital pulse captures the moment communication became a rigorous science. This framework remains the foundational blueprint, ensuring that every text, call, and data stream arrives with absolute integrity. Before Claude Shannon, the fight against static was a losing battle of volume and speed. This slide introduces the noisy channel funnel, a mathematical breakthrough that redefined the limits of communication. We see two distinct fates for data. When the transmission rate R exceeds the channel's capacity C, information shatters into useless fragments. However, Shannon's genius revealed a hidden path. By keeping the data rate below capacity and applying error-correcting codes as a protective shield, we can achieve perfectly error-free communication. This calculated redundancy allows us to transmit digital pulses through the most turbulent noise. It is the fundamental law that governs everything from deep space probes to the wireless signals in your pocket today. How do you weigh a whisper or measure the invisible? This slide introduces the formal scales of the digital age. Claude Shannon taught us that information is essentially the reduction of uncertainty, a concept mathematically defined as entropy. The table outlines our universal rulers, from the foundational bit, fittingly also called the Shannon, used in telecommunications, to the theoretical Nat and the historical Hartley, the unit Alan Turing used to crack the Enigma code. Finally, we reach the byte, the bedrock of modern storage. By mapping these logarithmic bases to specific contexts, Shannon transformed the vague feeling of knowing into a precise science. The more unexpected the message, the higher it scores on these mathematical scales. In 1950, Claude Shannon moved from mathematical theory to physical reality with Theseus, a mechanical mouse that became a pioneer of artificial intelligence. This slide reveals the secret behind the maze. Theseus was merely a magnet, while the true brain was a hidden grid of 90 telephone relays beneath the floor. We see the evolution of intelligence in two steps: the frantic dotted path of trial and error, transforming into the confident solid line of the learned phase. By allowing hardware to store and recall its environment, Shannon proved that machines could mimic behavioral learning. This whimsical experiment wasn't just a game, it was a historic demonstration that logic gates could navigate the complexities of the physical world. Enter the staggering complexity of the Shannon number. In 1950, Claude Shannon looked at a chessboard and saw an infinity greater than the universe itself. This slide illustrates the game tree, a branching explosion of possible moves. With 10 to the 120th potential variations, chess complexity dwarfs the 10 to the 80th atoms in the observable universe, making brute force calculation a physical impossibility. Shannon's genius was realizing that to win, a machine must do more than count, it must evaluate. By introducing minimax algorithms and positional functions, he taught computers to prioritize quality over quantity. This shift from blind calculation to strategic thinking provided the foundational DNA for modern artificial intelligence, proving that even in a sea of infinite choices, logic can find a winning path. Beyond the math lay the workshop of a legendary tinkerer. This slide reveals the playful soul of Claude Shannon through his most peculiar inventions. We see the ultimate machine, a mechanical hand in a cigar box that exists only to turn itself off, and the world's first wearable computer, a 1960s dress shoe wired to predict roulette outcomes. From the Roman numeral-powered TRJF Roback to robots designed to master bounce juggling, these toys were profound explorations of logic and physics. As Marvin Minsky observed, Shannon's engine was pure joy, For him, the harder the problem, the better the discovery. This collection reminds us that the architect of our digital world was, at heart, a man who never lost his sense of wonder. At the root of our digital existence lies a singular radical concept: information theory divorced data from physical meaning. This slide illustrates the expansive, interconnected legacy of Claude Shannon's genius. From this central trunk, branches extend into every corner of modern life, driving the compression technology of MP3s, ensuring the clarity of 5G signals from deep space, and redefining genetics as biological data processing. By establishing the foundations of relay logic and game tree limits, Shannon provided the essential architecture for artificial intelligence. He was the man who literally programmed the modern world, yet remained a playful tinkerer at heart. This final view celebrates a legacy where profound scientific breakthroughs were born from a spirit of pure, curious joy.